here. My name's Sean Maurer, mechanical engineer at the Smart Energy Design Assistance Center. Joining me today is Ryan Siegel, another energy engineer in our office. We're going to be kind of overviewing some key requirements for the 2018 IECC as part of our Energy Code training program. Today's webinar is being recorded and will be available on our website along with a PDF of the presentation. There are some controls on your screen. If you have a question during our presentation, please use the Q&A window. If you hover at the bottom of your screen, that window should pop up. If you put a question into the chat, we may miss it. If you put it in the Q&A, it'll pop up, give us a chance to answer it. So please enter your questions there. We'll also have some poll questions as we go through the presentation here. And I'll hand it over to Ryan to go through our introduction.
Well, thank you, Sean. As noted, we're here from the Smart Energy Design Assistance Center, housed at the University of Illinois. Just want to also make a note that attendees today will receive certificates of completion or certificates of attendance for today's session. Whether you are an ICC member, AIA member, or not, everyone will receive those certificates of attendance. So for self-reporting credits, for those of you who may need ICC or AIA credits, when we send you the certificate, you may go ahead and reply back to that with your member number so we can go ahead and get those reported in for you. We will note that AIA is running a little behind, so don't be too concerned if it takes a few days or even a week or two to register those credits onto your online system. So just so everyone's aware, as Sean noted, this is being recorded, and so you can go back and review it later. Or if you end up having someone else who may have been interested in the material, you can go ahead and send them over to our website and pick that up afterwards. So as we've moved from the 2015 to the 2018 IECC, International Energy Conservation Code is the basis of the Illinois Energy Conservation Code. I'm going to talk about some changes and identify some of the key compliance issues that we have observed in commercial buildings, along with looking to help people gain a better understanding as far as compliance with the Illinois Energy Conservation Code in the commercial sector. So we are housed at the University of Illinois at Urbana-Champaign. We are part of a public-private partnership in conjunction with the 360 Energy Group out of the city of Chicago. And our primary mission is to reduce the energy footprint of Illinois and beyond. So we are going to, our program is sponsored in part by the Illinois State Energy Office, housed at the Illinois Environmental Protection Agency, and so do want to go ahead and acknowledge their support of this program. So if people do have questions, we are here for providing technical support. You can email us the questions through energycode@sedac.org, or we do have an 800 number for use if needed. So that technical support can be anything related to the Illinois Energy Conservation Code and support of any projects here in the state of Illinois. So it could be building owners, occupants, design professionals, and code officials. We are here to support you. So we do have several online resources at our website, sedac.org/energy-code. Some of these are archived versions of our past workshops as well as webinars. We also do have several online on-demand training modules. These take approximately an hour to an hour and a half to complete, and it's self-paced for you. And those you can come back to if you need to stay for a time interrupt the training modules. You can come back and complete them later on. So that's several different things that we do have, and those training modules tend to be geared more toward a beginner end of the spectrum. So they're not designed for or don't have a basis in requiring people to have a very broad and deep understanding of the code to be successful in going through those training modules. So just a note, any permits that have been applied for after July 1st of 2019 in the state of Illinois should be under the 2018 IECC. City of Chicago went about a month ahead, so for theirs, it's permits applied for June 1st of 2019. So we're coming up on our 1-year anniversary here of full transition to the 2018 version. As far as one of the largest changes that we have seen is for anyone dealing with state-funded facilities, typically colleges, universities, Department of Corrections, and the like. Previous to the current transition, those facilities were required to use ASHRAE 90.1 for compliance. They now have the same ability and options as the rest of the state to use either the IECC or ASHRAE 90.1. So a little bit more flexibility going forward. We do like to call out some good practices when we find them, or other useful information. This is one of those, which is comes out of the City of Chicago Department of Buildings. And this is a compliance statement that goes along with permit applications for plan review. And this is very helpful. So even if you're not necessarily in the City of Chicago jurisdiction, this may be helpful to provide to the code officials as part of your design submittal. And calling to note the lower half there that allows the design professionals to check what the compliance method that you're using for compliance with the IECC, and it allows them information to determine what they're going to be looking for. So if you're marking that you're following the IECC prescriptive path, they know that they're not necessarily looking for your ComCheck report or a building energy model. So some very helpful stuff for design submittals. And rather than necessarily trying to remember and write down all the links, so there is online versions of the IECC along with the Illinois amendments, as well as Chicago's Energy Conservation Code and amendments. These can all be found through the helpful resources link at our website. We do like to call out that the International Code Council has done a very good job as far as enabling the search and find function on their website. So all their codes are made available for viewing at no cost. You can't necessarily copy and paste or print from there, but you can find the referenced sections very easily. So we do encourage people to utilize the online resources as they are available. We have had several webinars earlier this program year. We are coming up to the end of the current program year at the end of June. So we've had 5 webinars that have occurred earlier this year, and those are all archived here at our website as well. So, and one thing that we should make sure that we cover before we move into the actual code material is our first step, since today we're going to be focused on commercial applications of the IECC, is understanding if we're in a commercial building or a residential building. The IECC, the definition of commercial building is fairly easy in that it is not a residential building. So that could be commercial, industrial, and the like. And so for here in the state of Illinois, the definition of a residential building is a detached 1 or 2 family dwelling, or any building that is 3 stories or less above grade, 4 or less if you're in the city of Chicago, that contains multiple dwelling units in which the occupants reside on a primarily permanent basis. So a couple of factors there. 1 or 2 family or other multifamily in which we are dealing with primarily permanent occupants. So a couple of depictions here of commercial buildings. So those that do not meet the definition of residential, a motel, and we also have some commercial and warehouse type buildings. So these would all be commercial buildings. So, and with that, I will turn it over to Sean to continue on to the commercial envelope. Looks like we did have a question about K-12 schools. Here in the city of Chicago, those are being, K-12 schools are under the jurisdiction of the regional superintendents. The city of Chicago has gone ahead and adopted the 2018 IECC along with Illinois amendments and Chicago amendments. So they are following the same guidelines as the rest of Chicago. Around the rest of the state, I believe the adoption has not been as progressive, and I'd have to double check, but I believe it's the 2015 version, or they may have recently moved to the 2018 version of the IECC without amendments. So they don't have the amendments, where the city of Chicago does include the amendments.
All right, thank you, Ryan. So some quick things we'll be talking about for commercial envelope key compliance issues that we've run across. First is what buildings are exempt from the Illinois Energy Code. We'll touch on that briefly. And then we'll get into roof assembly compliance, insulation values, above and below grade wall compliance issues, fenestration issues, floor slab insulation, air leakage compliance, and then the component performance alternative, which is the UA trade-off you would be doing with a ComCheck type analysis. So what buildings are exempt from the Illinois Conservation Code? From the Illinois Administrative Code, buildings that are otherwise exempt from local provisions of a locally adopted building code and buildings that do not contain conditioned space are exempt from the Energy Code. A lot of times this refers to agricultural type facilities. So you can see an example of those. And then you can see these unconditioned storage houses here are also exempt. Within the IECC and the Illinois Conservation Code also spells out buildings that don't use electricity or fossil fuel for comfort conditioning. For the purposes of that definition, it is presumed that if you have over 100 amps of electric service, that there is electric heat comfort conditioning to that facility, unless a code official determines that service is necessary for purposes other than comfort conditioning. So that would be your definition of a building that is not comfort conditioned. And then buildings that are on the historic buildings register, either at the national level, a state level, or designated by local authorized personnel as historically significant, are also exempt from the provisions of the Energy Conservation Code. Within the IECC, language also extends to components of a building that are historically significant. So you can see an example here of this lovely Tiffany's dome. If other portions of the building were being upgraded, that dome itself is historically significant. It could be an isolated component of the building that would not have to be upgraded if the rest of the building did. So moving on to roof assembly and insulation requirements. New to the 2018 IECC, continuous insulation for above deck roofing insulation needs to have a minimum of 2 layers and the joints need to be staggered. This prevents some air infiltration through that insulation. It also improves that insulation continuity. For insulation that is underneath the roof deck on the interior of the building envelope, that insulation must be pressed against an air barrier to be part of the thermal envelope. Those have to be in intimate contact. Insulation that is sitting down on a drop tile ceiling does not count as part of the thermal envelope because air can move right through that. You don't get the thermal performance out of that insulation. Usually insulation in that position is used for sound dampening purposes and not as part of the thermal envelope of the building. Skylight curbs must have a minimum of R5 insulation in them, or the entire skylight assembly has to be an NFRC 100 labeled assembly for compliance with insulation requirements. Moving on to above grade and below grade wall insulation. Within the city of Chicago, they've removed section C402.4 in its entirety, and essentially has stated that it essentially removes the definition of what a mass wall is versus a framed wall. In essence, what they're trying to state is we don't care what the density of the wall is, it just has to meet the R value or U value requirements. They're not necessarily so concerned with the thermal capacity of that material, but it does introduce a little bit of complication in that you no longer have a definition of a mass wall to differentiate between mass walls and framed walls in that Chicago Energy Code. But again, it just comes down to a simplification of you have to meet those R value requirements or the U value requirements in the prescriptive tables to meet compliance. For below grade walls, new to the 2018 IECC, insulation used for C factor and R value compliance must follow those table values, and insulation must extend to 10 foot below grade or to the lowest level of the conditioned floor, whichever is less. So if your conditioned slab is only 8 foot below grade, your insulation only has to go down 8 feet. Moving on to fenestration requirements. The main thing we run across with window compliance is that this NFRC label is not displayed, or a certificate with these values is not displayed to the building code official. Usually most assemblies are compliant. That's not the issue. The issue is making sure that this certificate is available to the code official so they can verify compliance. So again, this label is going to have your U factor coefficient on it, your solar heat gain coefficient. For pre-assembled windows, it's usually stuck right on the window. So usually that's not the compliance issue. Usually it's for site-built windows. For those, the NFRC has a site-built program and a component modeling program to generate these certificates, and that certificate gets included in your construction documentation. Usually that is the component that's missing for compliance verification, and that's why many times windows don't meet compliance. Even if they are a compliant assembly, it's because that certificate has not been given to the code official. So we wanted to call that out and make sure that you are aware to call that out for your code officials and reduce that issue. This is an example of what that program looks like for generating those certificates. This is the component modeling approach software tool available through the nfrc.org website. And again, this presentation will be available, so you'll be able to have access to these links after our presentation. But once you generate this assembly in this program, that site build assembly needs to go through testing to verify it from an NFRC approved calculation entity, and then you've got an approved assembly. That certificate gets sent to you, you include it in your building documents, and your compliance is certified for your code official. Moving on to floors and slab on grade insulation. One thing we would like to call out, if you've got wooden rim joists in your commercial building, do not insulate those with fibrous insulation. It allows moisture to transmit through and can condense on that rim joist material, and leads to degradation, rot, and you can see highlighted here in the red circle some damage to that rim joist. Another thing to be aware of, floor insulation that's pressed up underneath your floor deck, however it's constructed, must maintain contact with the subfloor assembly. So you can see here a couple instances where that insulation is pulled away. It's no longer providing the insulation value to the floor assembly. It must maintain intimate contact with that air barrier surface in order to be effective. Some examples of ways to maintain that contact. Some wire ties pressed up between the rim joists is a fairly common method, although we will note that that does create some compression and will reduce the effective R value of your insulation. Another method is some strapping underneath the rim joists. So you create a cavity there that must be fully filled, or a mesh type system. Another effective method is spray foam insulation. Those are all good ways to ensure that your insulation maintains intimate contact with the floor assembly and with the air barrier of the floor. If you have a heated slab in your building, underneath that heated slab is required to have R5 insulation underneath the entire slab. And your perimeter requirement is increased from R10, 24 inches below grade, to R15, 36 inches below grade, or to the bottom of your heated slab. So if your heated slab is only 2 foot below grade, then you'd only need to go that 24 inches. For that perimeter insulation requirement, it can be on the outside of your foundation wall. As you can see on the far left here, in the center you can see kind of a floating slab assembly where that insulation wraps from under the slab and up the edge to create a thermal break between the inside and outside. It can also be a combination of horizontal and vertical insulation. If you do opt for that route of compliance, the combined depth of insulation and horizontal distance must equal the 24 inches for an unheated slab or 36 inches for a heated slab. So if you go down the minimum of 10 inches below grade, then you would have to extend out 14 inches for an unheated slab. That minimum 10 inches is for protection of the insulation that's below grade, so that it can't eventually over time be, as that soil erosion takes place and settling takes place, that insulation isn't exposed and susceptible to damage. The middle example, technically, this would be counted as continuous insulation for the slab that's going around the perimeter. You do have a slight discontinuity between the continuous insulation on the outside of the wall assembly and the continuous insulation on the inside of the slab assembly. It's a very narrow thermal bridge there, but it is a compliant method. It's not probably the best case example. We do recommend for foundation insulation that it is installed on the outside of the building. It provides some additional thermal and moisture protection to your foundation insulation, depending on the type of insulation you use. But that is a compliant method. Moving on to air leakage and air barriers, there are essentially 3 sections to the code dealing with air leakage through the thermal envelope. In section C402.5.1 through C402.5.8, they detail testing methods and means of compliance. The simplest way to achieve compliance is to do a building pressure test. If you depressurize or pressurize your building to a pressure difference of 75 pascals from ambient, that's equivalent to about a 25 mile per hour wind, your air leakage rate must be less than 0.4 CFM per square foot of envelope area. So this is not square footage of the floor area, it is 0.4 CFM per square foot of envelope area. While pressure testing is rare in commercial, it is gaining some traction. We're seeing it a lot in small commercial buildings. It's very popular in residential simply because it is a requirement in residential testing now. But we're starting to see it used in commercial, and it does help catch a lot of hidden issues in the building envelope that might otherwise be missed. So we do find that this is an effective means to do that air leakage testing. Another compliance method is to specify the use of air barrier materials, and in your plan drawings you must detail how those air barrier materials are going to provide a continuous air barrier, or you can specify air barrier assemblies. And again, your details must show how those assemblies are tied together so that air barrier is going to be continuous and unbroken. Some examples of some air barrier materials and assemblies. Fluid applied air barriers are probably the least common, most expensive, but the most effective, as it's very difficult to miss joints and leave gaps in that insulation when it's being sprayed on continuously across the building. Probably the next best method is the self-adhered membranes. When they're rolled onto a building and applied properly per the installation instructions, again, it's going to ensure that there aren't any gaps in that material that are going to allow air penetration. But probably the most common is the sealed and taped boards or building wrap. It's very, very difficult to get those properly sealed. It's very easy to miss a seam somewhere. With building wraps, if it's being installed over the course of a couple of days and some wind kicks up or something, it's not uncommon to see that material get torn or pulled away from the building in a couple places. It can be done effectively. It does take some additional work and labor to get that done properly. It can be an effective means, but we do see a lot of our issues with building envelopes using that method. Again, if you're specifying air barrier materials or air barrier assemblies in your drawings, you need to indicate somehow how that material is going to continuously connect to different assemblies. In this case, we're showing a detail above a window jamb. So you can see some call outs for the air barrier, how it's being transitioned, where there's some sealant in place to make sure that that air barrier is continuous. Very important to detail, especially complex joints in your building, tight corners, difficult to reach areas. You can see in the example picture here in the red highlighted circle, there was a detail with a couple of closely set I-beams that got missed. And this allowed a lot of outside air to come into an open plenum ceiling area, and the HVAC system could not keep up with that additional load. And so they had a lot of comfort complaints and humidity issues in this building. So very important, especially where you've got tight access areas or difficult or complex assembly joints, to spell out in your plans and drawings the details that are going to ensure that that is properly sealed. Another thing we've run across when using the air barrier materials is that inappropriate materials are used in some instances. Very common for wall to ceiling joints, that there's a little bit of a gap there between the roof deck and the wall that gets stuffed with fiberglass insulation. It should be spray foamed or sealed with a rubberized gasket or some other air barrier material. The code book does list acceptable air barrier materials in it, including common things like particle board, OSB, poured concrete, things like that. Some materials that you think might be air barrier materials but are not: ungrouted CMUs, felt paper, fibrous insulation. The main thing to be concerned with is spray foam insulation. It has to be the proper depth to count as an air barrier material. With closed cell insulation, you have to have greater than 1.5 inch for that to qualify as an air barrier. And for open cell, depending on the manufacturer, greater than 4.5 inches, and we've seen a couple manufacturers that has to be greater than 5.5 inches to count as an air barrier. So we do like to call that out as spray foam has gained popularity as a method to get quick air sealing for buildings. It does have to be the proper depth throughout the entire cavity that it's sprayed in, or if it's used as a continuous layer throughout that entire continuous layer. And our last section for the commercial envelope, the UA trade-off method. As the code R values and U values have increased over time, it's becoming much more difficult to have a UA trade-off that will have some negative impacts. But one of the things we like to call out is if you're using a steel stud building, you want to specify continuous insulation to break that thermal bridge for those steel studs. The code book does have an effective R value for steel stud wall assemblies table in it. And what we'd like to note is that for any of those assemblies, you're seeing a reduction of 30 to 50% of your listed R value in regards to what the effective R value is for that assembly, just because of the high heat transmissibility of those steel studs. What can happen in that situation, if you don't have adequate continuous insulation on the outside of the building, is you can develop condensation within the wall assembly, and that can lead to degradation of the assembly, mold growth, indoor air quality issues. And for drywalled facilities, drywall that with thermal bridging behind it can develop striping. in that finished surface on the inside of the building. As condensation forms along those thermal bridges, dirt adheres to it, and you'll get what are called ghost lines. So that's what you're seeing in the bottom image. There's those studs are creating a thermal bridge, allowing condensation to form on that wall, and you'll get those darker patches on the wall. So very important in your wall assemblies to ensure you're specifying enough exterior continuous insulation to ensure that you're not going to have any kind of dew point risk in your assembly. We do note that there is a helpful software. It's a free software called Woofy. It's developed by ORNL and a German envelope analysis group. And that program can give you kind of a basic analysis whether your wall assembly is at risk for moisture damage due to dew point and condensation. Before we move into the commercial section, we'll take a brief break here to answer some poll questions. Our first question is, what is not an acceptable air barrier material? We noted that in the code it calls out a number of them, and to be very careful about spray foam insulation depths. Question number 2, what is the primary reason fenestration products are deemed non-compliant with the energy code? Again, we called out in our presentation a couple things to be aware of, and we'll give a couple of minutes for people to answer those questions. Doesn't look like we've had any questions come into our Q&A during the presentation so far.
We have had actually some come in as far as talking about existing buildings, which most buildings that have renovations are part of. The code does not require existing buildings to be brought up to the present standard unless they're undergoing alterations or additions. And in the event that alterations are being done to a building, the system that is being altered or the area and the system being altered as part of the alteration does need to be brought into compliance. We have had several questions particularly regarding roofs. So there actually is a specific frequently asked question document on our website in regards to low slope roofs that we've had several issues on. But yeah, so if you're going through and doing a lighting upgrade, for example, the code does not require you to change or modify the building envelope for compliance. And similarly, if you're doing a HVAC project, that doesn't necessarily trigger that you have to do a lighting project as part of that. So it's just when you go to do alterations, those alterations need to fit the code.
Okay, we're going to end our poll here and share the results. Question number 1, what is not an acceptable air barrier material? Looks like most people got it correct, that 1.5 inches of open cell spray foam should be at a minimum 3 inches deeper to qualify, at 4.5 inches to qualify as an air barrier. All those other materials are currently listed as air barrier materials. And for question number 2, the primary reason fenestration products are not deemed in compliance with the energy code, again, looks like most people got that. That certificate or the NFRC 400 label is missing. So good job everyone on answering those, getting those correct. We did have a couple more questions come in about the envelope as we were closing out the poll question there. Does having greater than 40% glazing automatically trigger use of ASHRAE 90.1 in lieu of the IECC? For an existing building, no. Again, that would fall into alterations. If you've got an existing building and you're not changing that window area, or if you're just replacing glazing, then if you've got greater than 40% glazing, you can still use the IECC values for compliance. If you're doing a new building, I would have to check, but I do think ASHRAE allows slightly more window area per wall area than the IECC does as far as that percentage.
The IECC also has performance paths, which may also be used when you have excess fenestration as well.
R continuous value above roof deck in City of Chicago, is it still a minimum of R13? Um, I will have to check that.
I also have a question here about 7-story multifamily. Is that commercial code? The building would be a commercial, it would fall under the commercial provisions. There are some references when you are in residential occupancies that the commercial provisions will refer back to the residential provisions. So the building itself and the building envelope would be a commercial building envelope under the group R. But the interior spaces, there may be portions where residential provisions would be used, and those would have been referenced within the commercial provisions. So it gets a little tricky.
We'll have to we'll try to send an email about the Chicago minimum roof insulation. I'm not seeing a minimum R13 requirement, although I am remembering some text that may sound like that requirement. We will get back to you on that that particular question. Where can we find data for fenestration updated code requirements, since they seem to have become far more rigorous? The IECC tables list U factor, solar heat gain coefficient requirements, as does the ASHRAE 90.1, and also air leakage requirements for window assemblies. As far as testing procedures, there is another table that lists acceptable testing procedures, including the NFRC 400 testing requirements. So depending on whether it's a door, window assembly, a pre-manufactured window, there are a couple of different testing requirements to achieve those, but they are all listed in the 2018 IECC and in ASHRAE 90.1. I'm going to answer one more here, and we'll try to get to some more of these towards the end of the presentation. How are curtain wall assemblies unique in meeting thermal requirements? Curtain wall assemblies fall under the U factor and solar heat gain coefficient requirements for window assemblies. So the curtain wall assembly as a whole is treated as fenestration, except where you've got kind of shadow boxes built into that assembly. Usually they are met through a U factor alternative for those areas that are opaque within a curtain wall assembly, but where it is open glazing that is allowing daylight, that falls under the fenestration assemblies U factor requirements. Now we're going to move on through the HVAC section, and we'll come back to some of these other questions at the end of our presentation as we have time. But some key requirements for the commercial HVAC section we want to touch on. Requirements for when do you need to have energy recovery ventilation systems, equipment sizing, Economizer, fault detection diagnostics, system commissioning, duct sealing and construction, insulation requirements, when do you need to have demand control ventilation, protection of piping insulation, and circulation systems and demand recirculation systems for domestic hot water controls. So first, touching on energy recovery ventilation systems, we've simplified down two tables in the energy code that spell out, depending on the design percent outside air coming into the system as a percentage of your total system supply airflow rate, and your operating hours. At what CFM level are you required to have energy recovery ventilation? So you can see those tables summarized here. One thing to be aware of, energy recovery devices must recover at a minimum 50% of the enthalpy difference between outside air and the exhaust airstream going out through the system. And they need to have a bypass control that allows your economizer to operate around the energy recovery system. There's nothing worse than it's 55 degrees outside and you're trying to get free cooling, but your energy recovery system is running, warming that air up to say 70 degrees, and you're having to cool it back down to 55 before you discharge it into the building. So you need to have some way to bypass that energy recovery system. Most systems will have bypass dampers on them. For a lot of energy recovery wheels, there are controls built into them that can just stop the wheel from rotating, and that also qualifies as a bypass method. But one thing to note, there are certain instances spelled out in the International Mechanical Code where you cannot use an energy recovery device, and that is referenced by the IECC. In those instances, the main concern is you've got some kind of hazardous fume in the exhaust air stream that can be carried over into your fresh air stream. Most energy recovery systems have some bleed by of that exhaust air that can mix it back into your supply air stream. So when you've got hazardous fumes and things, they preclude the use of an energy recovery device because it can transfer over. However, you can still use a heat recovery device, as those are usually heat exchangers between the airstreams. The airstreams remain completely isolated from each other. I know in particular, 100% outside air systems for laboratories and hospitals will tend to have heat recovery systems instead of energy recovery because of the potential for hazards in those exhaust fumes. So these are detailing exceptions for having to have energy recovery ventilation where prohibited by the IMC. Again, that's going to call out primarily where you've got hazardous fumes in the exhaust air. Certain configurations of lab hoods with VAV setups and certain requirements. Serving a space that is not cooled or that does not have cooling and is not heated above 60 degrees. You do not need to have energy recovery. If greater than 60% of your outside air is heated by some kind of recovered heat or solar heat, then you do not need energy recovery. Systems requiring dehumidification with energy recovery in series with cooling. A diagram example of that is shown in the corner there, where your largest source of exhaust air coming out of a single point in the building is less than 75% of your system's designed outside air. The imbalance in airflows would make energy recovery infeasible there, and so it's not required. And then systems operating less than 20 hours per week and an outdoor air percentage shown on the previous page. Those would also be exempt from energy recovery requirements. Moving on to equipment sizing, very important that equipment is sized properly for the building. Usually the issue we see is that equipment is oversized for facilities, leads to short run times, which is hard on the equipment, results in lower efficiency and lower lifetime of the equipment. As far as what the Energy Code allows, you're allowed to have standby equipment to meet your N+1 requirements for design, so that you have a backup system in case one fails. You can have multiple units that exceed the energy load calculations for your building, provided there are controls that limit the operation of those units to match the heating and cooling load in the building. A good example of that is modular systems that have built-in controls. It's very popular now to have modular boilers in buildings. Modular chillers are kind of growing in the industry. But again, they have those built-in staging controls that allow your output of that system to match your sizing requirements. As far as how do you size that equipment properly, there is ASHRAE standard that's referenced in the IECC. There are also a number of software programs. We've shown 4 of them here on this page that can do that sizing calculation for you. They calculate your building loads and can also size the HVAC equipment. Moving on to fault detection and diagnostics. This is a new requirement to 2018 IECC that kind of expands on a previous 2015 requirement that systems be capable of doing this system. Now they have to be configured and it has to be working when the building is handed over to the building owner. Fault detection and diagnostics is important because if your economizer goes bad, it can lead to an excessive amount of energy use in your building that might not necessarily be caught for a long time unless you're doing some kind of system monitoring or you do commissioning down the road. So fault detection and diagnostics is trying to catch those kinds of errors before they result in a large increase in your utility bills and energy consumption. Those systems must be able to monitor supply, return, and outside air temperatures. provide status on key system operations, like is the cooling active, is the economizer active, is the damper open or closed for outside air. And it should be able to send a report to a centralized control panel when there is an issue to alert maintenance personnel that there's a problem that needs to be addressed. A couple of methods for meeting this compliance. On the right side of the screen is some thermostats. You can see under normal operation, it just displays your space set points and some general information. But if there's an economizer fault, changes the screen color and highlights on the screen that there's a problem. And another way to do it is if you've got rooftop units or other larger DX systems that are controlled by a central system, is to have BAS trending and automated alarms. Again, it's just some way to send an alert to a centralized location that there's a problem with the economizer that needs to be addressed. Moving on to maintenance information and system commissioning. There are a lot of points in the 2018 IECC mechanical section that changed the language from being capable of doing certain things to being configured and working when the building is handed over. This includes thermostat deadbands, setbacks for temperature set points when the building is unoccupied, the economizer operation, demand control ventilation. There are a lot of controls set up in the code now to try to optimize energy efficiency of buildings. With increased complexity comes an increased need to make sure that complexity is going to work properly. Unfortunately, what we find with a lot of buildings, since commissioning is one of the last things done for a building, as timelines get short and as budgets get short, commissioning often gets reduced or cut from the budget. And that can lead to a lot of long-term issues and increased energy costs. And also callbacks to the mechanical contractors and designers of the building. So it's very important, if at all possible, to ensure that commissioning is completed for the building. Some examples of how you would show that compliance. These are some examples of forms from a Texas authority. In section C402.4.1 of the IECC, it spells out preliminary commissioning report. What should be included in there, and includes things such as air balancing, system details, but it spells out in that commissioning report, it should be completed by a commissioning agent or an authorized designer. That initial report needs to be presented to the building official before the certificate of occupancy can be given to the building owner. That initial report is going to have an initial list of deficiencies that need to be corrected and how they should be corrected. As far as detailing in your plans, what kind of commissioning needs to be done, usually on plan drawings there will be a page that details sequences of operations, either in the book or in plan drawings, that are included for the code official to review and see that there are commissioning examples of what needs to be done to verify the systems are working. And then these are some compliance certificates, signatures that verify that that testing's been completed and is going to be fully completed for the building owner. Moving on to duct and plenum sealing and insulation requirements. Supply ducts and return ducts and plenums shall be insulated to not less than R6 when located in an unconditioned space within the building. Where located outside the building, that insulation should not be less than R12. Ducts, air handlers, filter boxes should all be sealed. For residential, there is a requirement for duct leakage testing. It is not required in commercial buildings except for high pressure ductwork. That is ductwork that's going to operate at greater than 3 inches of water column pressure. This is a particularly bad issue when you've got leaks in the supply system, when you've got unducted returns above the ceiling. In that instance, your supply air doesn't make it into the space. It gets shortchanged straight back to the air handler. And so you're circulating air through the building without getting the benefit of space cooling and conditioning. It just increases your fan power and energy consumption. Some other issues that can result, as you can see in the image here, that thermal image, there is a duct joint put together there, and cold air is blowing out on the outside of the insulation wrap. Now you've got a dew point condensation risk there as well. So very important that ductwork is properly insulated and sealed. When sealing ducts, you should make sure that the joints are sealed duct to duct and not to the outside of the insulation, and not anywhere that's going to create an air gap for leakage to occur. Please don't use duct tape to hold ducts together. I know it's been used in the past, but as you can see, that adhesive dries out over time, turns into powder, and then those joints fall apart. So if you're going to be holding ductwork together with an adhesive material, it needs to be UL 181 rated mastic or tape. Anywhere where you've got a transition between duct materials is often a failure point. In the image on the bottom right corner there, that's actually a round hard duct insulation with the exterior wrap transitioning to some flex duct. And again, you can see they tried to hold that together with some duct tape instead of proper fasteners. So that's where you want to be particularly careful to make sure your ductwork is properly sealed and held together. Moving on to demand control ventilation shall be provided for spaces larger than 500 square feet with an average occupant load of 25 people or greater per 1,000 square foot of floor area. So what we're looking at here, in the picture, you can see that yellow block is if you didn't have demand control ventilation and you were bringing in continuously your minimum ventilation rate. It's very energy intensive to condition outside air to the temperatures and relative humidity that we want for inside air conditions. The most common way to mitigate that is with CO2 sensors. You can see that's the green line in the front. The CO2 sensors pick up when people are in the space and exhaling CO2 into the space, and your system can react and bring in more outside air to offset that and ventilate that air out. Places where you do not need to have demand control ventilation, if you've got full energy recovery complying with the energy recovery section of the code, then you do not need to have demand control ventilation because you're going to be recovering most of that energy that you would be exhausting out anyway. If you've got multi-zone systems that do not have a centrally controlled control system, so if you've got electronic thermostats and controls in the building, but they're controlled space by space and don't communicate to a central control panel, then you do not need to have demand control ventilation in that instance. The main concern there is air balancing between spaces and making sure that you're not creating pressure problems. And then if you've got low outdoor airflow rates or low supply air rates to a space, that 1200 CFM requirement there for points 3 and 4. And then if you're providing ventilation solely for process load requirements, those are all instances when you do not need to have demand control ventilation. Some common issues that we see with demand control ventilation, first and foremost, is the economizer is not set up to override the DCV. So you've got an opportunity to get free cooling from outside air, but your demand control ventilation is saying I don't need outside air, and so it locks out the economizer. It should always be set up so that the economizer can override the DCV and give you that free cooling when it's available. Another issue that's very common is there are two different ways to do set points for CO2 sensors. There's either a total set point where it's reading the total CO2 concentration in the space, or a differential set point. For CO2 controls, all settings are based on a differential set point of 700 parts per million beyond ambient. In most cases, when you've got a fixed set point for a CO2 sensor, you're going to see that setting at about 1100 or 1200 parts per million in the building. And that's based on ambient CO2 being somewhere between 400 and 500 parts per million. So be cognizant in your buildings. If you're not using a differential set point for that CO2 setting, be very careful that that fixed set point is correct. And also, if you've got a differential, be very careful that they're not using a fixed set point as the differential, or you'll underventilate the building. One other thing to be aware of, for demand control ventilation, there are instances when it's particularly cold outside where that can cause an issue with the air handler tripping a freeze stat. So you do want to have some protection in there for low temperature protections. When it's particularly cold outside, you want to limit how much outside air you bring in. Protection of piping and insulation. Usually large chilled water lines and steam lines, hot water lines that we see do not have this problem. This is usually a concern for smaller refrigeration lines on DX systems and VRV systems. It's not uncommon to see this pinch wraparound foam wrap on those lines. And the main concern is where you've got brackets that hold it together. Very often those brackets go straight to the copper line instead of wrapping around the foam. In corners, stress on that foam can split the seams open and leave it uninsulated. And UV protection is a particular issue for these. Sunlight and UV degradation turns this foam into powder over time, and then it isn't effective for its purpose. So these are some examples of how to do that properly. Miter your joints to prevent the buildup of stresses on an insulation, keep it sealed. Hangers and support brackets for those lines wrap around the outside of the insulation and don't expose that pipe. Having some kind of UV protective wrap on the outside of that insulation to protect it from the weather and direct sun. Those exterior wraps do need to be removable for maintenance purposes, so be aware that tapes and adhesives directly on the outside of that insulation is prohibited by the IECC. It needs to be some sort of removable exterior wrap or coating. Finally, we want to touch on circulation systems for domestic hot water. Whether you're doing a circulation system or a demand recirculation system, if you've got these in your building, they have to have a demand-based command for circulating that water. So the pump should be off once your loop is at temperature until there is a demand detected in the building. One of the concerns we usually hear about this is Legionnaires' Legionella. If you're stopping the circulation in the system, is that going to create a concern? What we find for most commercial buildings is that there is enough active use in the building that you don't get stagnant water in the building for long enough to create an issue. So these are just some examples of what those types of loop systems look like. On the left, you've got a dedicated hot water loop for recirculation. The pump is usually backed by the water heater, circulating out into the building. And for the demand recirculation system, there is an additional limitation here since it's recirculating back through a common return cold line. That common return cold line cannot exceed 104 degrees Fahrenheit. That way, when that pump shuts off, if you turn on the cold water, you're going to have access to cold water right away and also limit that Legionella risk. And now, before we move into the lighting section with Ryan, we've got one more poll about mechanical demand control ventilation requirements, which is not an exception to the requirement for demand control ventilation. Systems having full energy recovery, multi-zone systems that do not have a central control panel. You can go through the rest of the options there, and we'll try to touch on some of the questions that have come in through the mechanical portion. Do we think recovery wheels will go away given the concerns over COVID-19? I do not think they're going to go away. There are some provisions and some recommendations from the CDC and ASHRAE to, as long as it's permissible for the building system, to increase outside air to try to dilute any kind of germs or microbes in the air in the building. But really, when it's very hot outside, very humid outside, you're still going to want to use those energy recovery wheels to keep your system from being overwhelmed and unable to maintain comfort conditions in the building. Because one of the issues with COVID-19 is if you've got thermal stress in the building, that can increase your susceptibility to the virus. So I don't think they're going to go away. I do think that there are going to be some limited provisions and things for increasing outside air ventilation on an as-able basis.
And similarly, we may see a slight design modification with increased use of purge sections to substantially reduce any risk of carryover from one side to the other.
Then we got another question. Does mechanical section C403 apply to direct replacement like-for-like equipment? For example, a rooftop unit on an existing building that's being replaced. To our understanding from what we read, that falls under the alteration section in C503, I believe. Yeah. Where you would have to do a sizing calculation to properly match that new unit to the building's loads. So C403 would apply there. And we've had that question come in a couple of times recently, like for like equipment replacements. They do have to be properly sized to the building's loads as best as they can be determined.
And similarly, with those, the new unit may also need to have such things as the economizer or the economizer controls and the like. It would not require a building automation system or anything like that to be installed and require additional HVAC units to be tied together for those controls. But the unit that is part of the alteration would need to be in compliance with that. And similarly, when you do a quote like for like replacement of HVAC equipment, it is not uncommon to see that equipment being 10 years old or older. Loads have changed over the years, particularly as buildings have been improved. It's not uncommon where you'll during that time a lighting upgrade will have been done or a space usage has changed. So the load may change over time. And so the unit that was there, the new unit may in fact be larger than the existing unit is. That is possible. Frequently it is smaller, but just a like for like replacement, you do have to verify that the new one is correct.
And it looks like most people got the poll question correct. Spaces with manually operable windows are not an exception for demand control ventilation. So good job everyone on getting that correct. We'll let Ryan take over for the lighting section.
All right, well thank you, Sean. So we're going to cover a handful of items here, the last 6 items for today. And so starting off with occupant sensor controls, we've got automatic shutoff is required in nearly every space. These can be either with occupant sensing devices, which could be occupancy sensors or vacancy sensors, both of which sense occupants, or time switch controls, or you can have both. But nearly every space you have to have one or the other. Occupant sensor controls, they continue to expand this over time. This code cycle, they've added open plan office areas, and they handle this in a couple of ways. They have 3 space types: open plan office areas, warehouse storage areas, and everything else. So starting with the warehouses, here we have a 50% reduction that has to be required, that has to be achieved, at least 50%, 100% is acceptable. We also need to control aisleways separate from the open areas and not overlap. So here in this depiction here, if we have someone in the row on the right, we don't necessarily need the aisle lights in the other rows to be on for that person to properly pick their order. So moving over to open plan offices, first of all, the definition is it has to be over 300 square feet in order to qualify as an open plan office. Otherwise, that is considered a private office. So for these, zones can't be larger than 600 square feet. Now the sensor area, the sensor coverage may be nominally more than 600, but each lighting zone can't be larger than 600. And these next 2 kind of come in tandem, where we have to reduce the lighting power by at least 80% when a zone has no occupancy, and the remaining 20% has to go off within 20% of all the zones being unoccupied. So this can be done one of two ways. The more common way, and perhaps the easier way, is the occupant sensing device just controls 100% of the lighting in its zone. And so when a zone is unoccupied, all the lights go off and you're done. This doesn't include lighting for safety and security. So this is just the controlled lighting. And then by virtue of controlling 100% of the lighting in its zone, by doing that, all the lights will be off whenever all the zones are unoccupied. Alternatively, you can tie all the sensors together so that each sensor controls at least 80% of the lighting in its area, and then the remaining 20% is triggered once there is no longer a call for lighting in any of those zones. So the last point here kind of makes sense, that the daylight responsive controls only activate if there's occupants present. We don't want the building at night to turn on all the lighting in the daylit zone just because, well, it's dark out. We want to make sure there's people there, and then the daylight harvesting controls come over top of that. So we'll talk a little bit more about daylight harvesting a little later. So now that we've covered warehouses and open plan offices, now we're going to cover everything else. So noting 20 minutes, previously this had been 30 minutes, so this is getting shorter with time. LEDs don't have as much of an issue cycling as the older fluorescents did, so not as much of a deal here. Now this is where you get into manual on, or if it is auto on, so typically manual on is called a vacancy sensor, auto on is called an occupancy sensor. Now if it is auto on, it can't bring on more than 50%. The other 50% you have to give, the occupants have to indicate they need some more by pushing a button or some other mean or method. Now, they do allow it to go to 100% for corridors, stairways, restrooms, primary building entrance areas, lobbies, and the like. Or, again, safety and security will come on through this. And the important thing here is for all these areas, there needs to be a manual control to allow occupants to turn the lights off. Early in my career, had a facility, it was the latest and greatest, and so they put occupancy sensors everywhere, so you didn't have to worry about turning on and off light switches. Problem was in meeting rooms, when you went to show something on the screen, there was nowhere to turn the lights off so you could actually see what was being displayed. So a little bit of a difficulty there. So having that manual off is important. So next up, moving over to time switch controls. So where are these required? Step one, areas not provided with occupant sensor controls. So what this says is if you have time switch controls required and you use occupant sensor controls, that is okay, and you don't need the time switch controls for those areas. So you can trade in that direction. You cannot trade in the other direction. So if it says you have to have occupant sensing controls, you can't install time switch controls in lieu of the occupant sensing controls. So I do call out a few exceptions for these. So number one being where patient care is directly provided. So you can, this is not just any healthcare facility, this is specifically where the patient care is being provided. Typically these would be, hospital bedrooms and things like that. So, occupant safety and security, and similarly, item 4 on here, shop and laboratory classrooms. So we don't want to shut lights off where it could endanger people. Code does call out several functions that time switches have to have. One of the biggest things here is item number 4 is have to have a program backup of at least 10 hours. This doesn't necessarily preclude manual time switch controls. However, there has to be some backup power supply to keep that running for at least 10 hours. And another large one is the holiday shutoff, to be able to skip the program for 24 hours. Those two are probably the more common difficult ones to get. If you have time switch controls, then you have to have light reduction controls. And so here, occupants have to be able to reduce the lighting by at least 50% reasonably uniformly. Now that can be 100%, but they have to be able to get at least 50%. So now here, if you don't want to add the additional complexity for light reduction controls, you can do so with high efficiency illumination and get that under 0.6 watts per square foot for illumination. So by saving those watts up front, you have achieved that energy reduction without having to add that complexity. So, and again, here you see the corridors, lobbies, mechanical rooms come back in, very similar to the occupant sensing, where it allows for 100% illumination. All right, daylight responsive controls. Here, it's a little unusual in that we're covering the exception, and that is by reducing your connected lighting power, you are allowed to forego the daylight harvesting controls. So it's a 40% of the weighted average that is in the daylit zone. So if you are below that threshold of a 40% savings, you don't have to purchase, install, commission, and maintain those controls. So a couple of examples. Here in the first example, 50% of the square footage is in the daylit zone. So therefore, I need to be able to reduce by 50%. I need to reduce that 40% by at least 50% or 20% less. So in this first example, ordinarily my budget would have been 158,000 watts. If I get it below 126,400, then I'm finished with daylight harvesting controls. Don't have to buy them, don't have to put them in. In the second example, a quarter of it. So I have to reduce my 40% by 1/4 or 10%. So in the second example, 142,200 is my target. If I get below that, I'm done. This 10% will come back in a little bit. Exterior lighting controls. Here we break it into two segments. One is general exterior lighting, and the second is decorative. The decorative being facade and landscape lighting. So for both exterior and decorative, we have to have daylight shutoff. So we have to have a photocell or some other means to identify, do I have enough ambient light that the exterior lighting is not adding benefit. The other thing that they both must have is a time switch functionality or occupant sensing functionality. And depending on where you are, whether you're in general exterior or decorative, we'll tell you what the timing has to be for either a shutoff or a setback. So facade and landscape lighting, we have to shut it off. For general exterior lighting, we have to set back or reduce the connected load. So, and what we're trying to do is we're trying to prevent what we see here in this picture. You know, a bright sunny day, that parking lot light is not adding any benefit to the parking lot. Also, something else to be aware of is particularly with LED fixtures, they are sensitive to heat. And so we want to make sure to not be operating them during the hottest part of the day, which will extend their lifespan too. So a nice benefit of having that is to extend the life of your facility. So decorative lighting needs to be turned off within 1 hour of the closed business and cannot turn on more than an hour before opening. So this 1 hour, you get an hour on each end so that it can continue to, you know, while people are likely around, you know, we still have our lighting, our decorative lighting in place. Now for general lighting, we have to set back by at least 30% during one of the following times. Either midnight to 6, or similarly 1 hour before or after business, or any time where activity has not been detected for greater than at least 15 minutes. So with that, if you decide to do the 1 hour of open and close, you can have just a single time switch functionality to cover both. If not, you are likely to require 2 different time switches. So, functional testing, similar to the mechanicals, functional testing and commissioning is very important for lighting. We have increasingly made the lighting controls more complex, and so with that, we have to make sure that we commission those controls to verify they're working as intended. So with that, this is done by the registered design professional, has to provide the evidence of testing. Testing could be done either by a controls contractor, lighting supplier, registered design professional, commissioning agent, or any number of other people. But they are responsible for securing the evidence of that testing. And we have to do it on all our systems: occupant sensing controls, time switch controls, and daylight responsive controls. So again, that third one, if I can avoid having to install them, that's one less thing I have to do commissioning on. The other thing is we need to provide the O&M manuals and the report to the owners within 90 days of the certificate of occupancy. Commonly, how we have seen this enforced is by requiring a letter from the building owner acknowledging that they understand that they should be receiving this within 90 days of the certificate of occupancy. Realizing that the authority having jurisdiction and the planning typically are not involved beyond the certificate of occupancy date. So at least by acknowledging that the owner understands they should be looking for this, if they're not turned over, they know to go look for them. So occupant sensing controls have to test every space geometry and sensor combination. This is likely going to require testing nearly every space, because in order to have the same sensor geometry and room geometry, it has to be identical. So if you have mirrored image rooms, that still does not qualify. So you'd have to test both of those. So, and it calls out several factors that we're checking for. Similarly, time switch controls, do we have the proper schedules involved? Have they been set up correctly? Is the battery in place, or whatever the backup power supply is, and verifying that the override time limit times out correctly. So, and then as you're going through daylight responsive controls, you're again having to go through and set up each individual room and verify the calibration on that. You know, this can be very time consuming. Reduced lighting power. So this is one if you're going through the prescriptive requirements, which may also include a COM check, which would be a prescriptive path. One of the things is you have to have a bonus measurement or a bonus feature. And so one of these can be reduced lighting power. Again, this comes back to that daylight responsive controls. I know that 10% would come back. So if we have total connected power less than 90% of the allowance, we have satisfied this requirement of bringing our building up to 11. So with that, I think we do have a final couple of poll questions here for lighting, along with some more questions that have come in. So first is, what is required for exterior lighting controls? You may choose more than one here. And secondly, which systems require functional testing? You can choose more than one there as well.
Lighting question that came in: how does exterior controls impact commercial properties that operate 24 hours? such as multifamily and hotel properties?
That is an excellent question. How do you determine the hours of operation of the business? For hotels and motels, what we have commonly come across the interpretation being is, when is the front desk open? Again, for these properties, you may end up where some properties are continuous operation, and so the time switch, the hour before, hour after opening and closing doesn't really have relevance there. Now, I must also note that sometimes properties are installed and designed 24 hours and later become no longer 24 hours. So it might be wise to at least design easy provisions to make a retrofit easy to accomplish later. One example here is there's several large retail locations previously were 24 hours, and even before the COVID-19 had been trimming back their hours and decided, no, we're going to go ahead and close from, say 11 p.m. to 6 a.m. So making that flexibility easy to achieve would be wise anyway.
Okay, looks like we're still getting a few answers to our poll questions. We did have one more regarding functional testing. Is the design professional performing the testing?
Yeah, the testing can be done by the design professional. The design professional is responsible for making sure the testing is performed. So it could be done by the design professional, could be done by the manufacturer of controls, a commissioning professional. Any number of people can do it. They're just responsible for verifying that it was carried out. And they're also responsible for making sure that the process and procedure was documented.
All right, we're going to end our lighting poll here, share our results.
All right. Required for exterior lighting controls, time switch or occupant sensing, yes, and daylight controls, yes. So we got, yeah, most people picked up on that both of those are required. And similarly, for which systems have to do functional performance testing, all of the above. So most people got a fairly good response on that. But yeah, so you have to functionally test all three of those, and lighting controls, you got to have time switch and daylight harvesting.
All right, we've had a few other questions come in from other sections of the presentation today. One we got here is, how are single tenant renovations that include mechanical system work in multi-story buildings affected by the energy recovery, ventilation, and economizer fault detection and diagnostic requirements? So if you're doing an individual tenant unit work, usually you're not going to be changing the central exhaust fan or the central HVAC system. And so those would not trigger updates to be in compliance with energy recovery, ventilation, or fault detection and diagnostics. If you've got individual units that have individual exhaust fans and individual HVAC systems in them, usually they're going to be too small to fall under the economizer fault detection and diagnostic requirements, and similarly for the energy recovery ventilation requirements. There's also the potential there that with multiple exhaust fans in a small residential unit, you're not going to be exhausting 75% of your outside air requirement through a single exhaust port. Is also another potential thing there that could preclude the use of energy recovery ventilation. Question on the lighting section, any special provisions on occupancy sensors in restaurants?
As far as occupant sensing controls for restaurants, looking through the code here, the list of C405.4 some of those that may be may need occupant sensing controls would be things such as enclosed offices, restrooms, and maybe other spaces 300 square feet and less, enclosed by ceiling, floor to ceiling height partitions. So there's no special requirements for those. Just noting which spaces. Generally, the main dining area is not likely to be 300 square foot or less. So there's only certain spaces, but they would still have the same 20-minute delays and things of that nature.
Okay. We do have one final poll we're going to launch here for everyone at the end of our presentation. We're still going to take a few more questions here in another 5 minutes or so. We have a question here about the provisions for an alteration to a building. Would the existing building need to meet the new code if only part of the building is being altered? Is there a percentage that triggers that? Is the building also having an addition? Will that trigger the existing building requiring an upgrade? So for existing buildings, if you alter the existing building, you do not have to bring the entire building up to the code. Whatever you're altering, like say you open up a wall cavity, it does not need to be brought up to the code requirements. You just need to fill that wall cavity with insulation. If you're doing an addition onto a building, again, the existing building does not need to be upgraded to the code, but the addition does need to meet the prescriptive requirements. So alterations don't require the entire building be brought up to the current code. They require that the components that are being altered or changed be brought up as close to the code as is feasible without impacting the safety or integrity of the building, or overstressing any of the building components. So you can't put in more insulation than you're capable of putting in a wall, for example. Or you couldn't add, say, more equipment to a roof that isn't built to support that extra weight. Some considerations such as those.
Something else coming up, I do want to let people know today was the commercial segment of content. There is a residential provisions that we'll be covering next week. So if you are interested in residential provisions, go ahead and feel free to pop over to our website and sign up for that as well.
Okay, we've got a question here about, is the term heated slab only related to when hydronic heat lines or other sources are within the slab, or when there is forced air present in a basement space not specifically directed at the slab? It is referring to hydronic or electric radiant heat within the slab itself. If you've got a slab over a basement area that has radiant heating in it, only a portion of that that's on the exterior of the building would require extra insulation. If it's all interior to the building, since you've got a conditioned space below and above it, you would not have to have additional insulation for that slab. If only the exterior perimeter that's touching exterior space would have to have that additional insulation requirement.
Yeah. The only other place with that, it also notes if you do have hot air distribution system that is in contact with or placed within or under the slab. We don't typically see ductwork run under a slab, but we have come across that before. But yes, so just a slab in a heated space would not qualify as a heated slab.
Question about codes in the long term. Is there any currently underway to consolidate the building and energy code, so we're referencing only one code?
I haven't seen any move in that direction. What we have seen in codes in general is they are trying to do a better job of cross-referencing rather than reiterating, such that you don't end up with discrepancies between codes. Instead of doing that, the code will just refer over to the other code. And something, as I recall, in the back of the codes, they actually do let you know what other codes and sections are referenced within it. So yeah, it's similarly, there isn't been a move towards consolidating, say, the building code and the fire code. So we haven't seen that.
Just a reminder that we are recording this presentation. We will be uploading it to our webpage at the end, probably within a couple days after this presentation. And there will also be a PDF of the slides available. We do have a question here about, it's a question we've got a couple of times. When running dew point analysis for a wall with continuous exterior insulation within the framing, it seems really hard to avoid having the dew point fall within the wall cavity. We've actually got this question a couple of times, and it can be difficult. We're actually going to try to do some analysis on what level of exterior insulation do you need relative to how much cavity insulation you have to prevent having condensation risk within your wall assembly. But the main thing to be concerned with most of these wall assemblies is that it's almost impossible to prevent having some portion of the wall assembly having some dew point risk. The primary concern is having some way for that wall assembly to dry out. So you don't want to have a vapor barrier on both sides of your cavity where you end up locking that vapor within the wall cavity where it has no way to dry out, and you end up having mold and degradation risks then. We are looking into how much relative exterior insulation do you need relative to your cavity insulation to prevent dew point risk. The more cavity insulation you have, the more that exterior sheathing is going to drop in temperature and the greater risk it's going to have. So the more exterior insulation you would want to compensate with. So we're trying to look into that a little bit and come up with some answers for that we'll post. And then one last question that we've got here: how does the IECC respond to ventilated rain screen cladding in terms of thermal performance? I will have to do a little digging on that. But to my understanding, that ventilation layer tends to be towards the outside of any continuous insulation of that rain screen cladding. I don't know, Ryan, have you run across any details on that?
Nothing specifically. Again, the important thing here is to look at where is your thermal boundary for that. So yeah, in a ventilated rain screen, typically that would be outboard of your thermal boundary or your thermal envelope, and that is more in your bulk moisture control layer. So again, you have air control layers, vapor control layers, and bulk water control. So being aware of how those interact with one another. The code doesn't call out any specific types. Again, we want to focus on performance and looking at that.
Okay. And then one last comment. CEUs for this, for AIA credit. Once this presentation is ended, within a couple of days, we try to send out a certificate of completion. Reply to that email with your AIA member number, and we will submit that for you. Thank you all for attending today. We hope it was an informative presentation, and have a great afternoon.